Great. So, welcome, ladies and gentlemen, to today's welding presentation. We are going to show here a demonstration of a rail welding process with our aluminothermic SKV process using thermit. The process is used worldwide to weld two pieces of rail in all circumstances, and we're going to demonstrate how this is being carried out. So the first step is to create the molds, or to put the molds around the weld, and to seal these molds with luting sand. And the reason why we are using luting sand is that the steel that is being created is going to be liquid. It's going to be liquid steel that pours into the gap, and it is as liquid as water, so the viscosity is very low, but it's obviously as dense as steel. So we will have a liquid with the density of about 8, and it's about 1 liter, so 8 kilos of steel that is going to be poured into the mold. And obviously it's extremely important that this seal is absolutely tight and that there is no spills or nothing that gets out, or that any of the sealing gets washed away, to protect the rail on both sides. Because if there is a spill, then obviously the weld would have to be cut out and recreated, because it would destroy the surface of the rail. So it's not just about being practical, but it's about the safety of the process and the reliability of the weld. The sand is being used, and also the mold is created out of sand with obviously some additions, because it has an incredibly high tolerance to temperature. The steel that is being poured out has about between 2,000 and 2,400 degrees Celsius. So the mold really needs to be able to hold that steel into place and to keep it where it needs to go to weld these two pieces of rail together. The sheet metal is used to cover the rail to protect it against any spills of the slag, not the steel. The steel is going to go into the mold, but obviously the slag that is also being created through the aluminothermic process then has to escape, and it will end up in the slag pans to the side. Obviously the temperature will be the same. It will also be around 2,000 degrees, which is why the slag pans have to be preheated and also protected with sand. And if there would be any spill, any droplet or anything, we want to absolutely avoid that hits the top of the rail, because that would create a change in the structure, in the microstructure of the rail steel, which we obviously want to avoid. The next step is the preheating. So we need to preheat both the mold and also the ends of the rail, because if we would pour the liquid steel into the mold immediately, then the rail steel, would suffer an immense temperature shock from outside temperature immediately onto the 2,000 plus degrees Celsius, and that would create tension in the steel, which we obviously want to avoid. So we need to preheat the steel to then allow the steel to enter the mold and then the mold be around 1,000 degrees Celsius. What you What you have just heard is our newest invention, the Smart Weld Jet, the preheating device. It's an automated preheating device that uses air instead of oxygen, which is the currently used method. And it's immensely powerful, as you have heard, because the preheating process is extremely important for a reliable quality of the weld. So the colleagues have just initiated the thermite reaction. Inside the crucible now there is the aluminothermic reaction, so it's a reaction between aluminum and iron oxide that has a lot of chemical energy to heat up the steel to about 2,000 degrees, and now the steel is entering the molds, and the slag, which is aluminum oxide, liquid aluminum oxide, is pouring into these slag pans to the side. To show you how that usually looks, we have prepared a video where you can see this reaction on with and without the filter, the Enviro filter. You didn't obviously see anything about the reaction or any flames coming out of the crucible. On the right side, you see how it would look without the filter. So entering the filter, putting on the filter, takes away 99% of all the exhaust and all the fumes that that come out of the reaction, the aluminothermic reaction. And now inside the mold, that's where the magic happens. So right now, the liquid steel actually melts several millimeters of the rail and creates a fusion zone where the two pieces of rail now become one continuous rail. And obviously, rail steel is very hard, very delicate, so the microstructure is being reproduced by the thermit steel, so that in the end, the weld has the same properties, both in terms of hardness and also the mechanical properties of, at least, of the rail that surrounds it. Every process has a defined waiting time, a defined preheating time, and the devices obviously are pre-programmed to have these heating times and the cooling times so that the energy that is being used into the weld is perfectly balanced and understood, so that we get exactly the microstructure and the substance that we require. It's necessary to respect these times so that the steel can undisturbedly create the bond between the join between the two pieces of rail. And after a few minutes of waiting, we will then see the colleagues displace the mold, take the mold out, and then treat the weld, as we will see in a few minutes. At the low end, obviously, we want the steel to be already settled. But if we wait too long, the steel obviously over time gets harder and harder and harder. And we certainly want to be able to take away the excess steel in a state where it's still soft and possible without too much force or too much disturbance for the joint. Ideally, we cut the mold head when it just solidified. So when it's just past the liquid phase, we certainly do not want runouts, but we want it to be as soft as possible to then be able to shear the weld in the best possible way. This is the way that we want to see it. So it's still glowing hot, it's still soft, but there is no liquid phase. And then we have the opportunity to perfectly shear the weld with this battery-powered weld shear. Obviously, there is excess steel to accommodate, to make the process as robust as possible. So, sometimes the cuts are perfectly parallel, the gap may be slightly wider than it's supposed to be, so we always need a little bit extra to make sure that under any circumstance the weld will perform well, and that extra steel obviously needs to be taken away. So the weld shear now cuts into the steel that is still soft, but obviously solidifying very quickly now. The pressure of the weld shear is extremely important. So this is a powerful unit. It's about 20 tons, at least 20 tons of pressuring force to be able to cut the steel under any circumstances, smoothly without disturbing or destroying the weld. So once the specially hardened and pre-prepared blades have cut the excess steel away, we take it off and bring it to the side. And now the weld is already performed. The last step of the welding process is now to grind it, to smoothen the surface. And for this, several grinding machines are on the market because different welding crews are used to their equipment. And what we show here today is a standard grinding machine, as it can be seen in several markets, that we have retrofitted with a battery-powered upgrade. So usually these machines are powered with gasoline engines or diesel engines, but obviously they're smelly, they're loud, they're unreliable, and we offer this battery-powered grinder to be able to grind it. And as you can see, it's very quiet compared to the original products, and it doesn't have vibration, and it's very reliable to use. So the hot grind, which is called hot grind because the steel is still hot, is the first step. And it's very efficient because the steel is still hot. It's not very hard, and we can grind it, and it's very quiet and can be used. And then it needs to cool off, and after it's being cooled off, the precision grind can then be applied using the same machine. But obviously it takes a few minutes up to an hour for the steel to be cold enough to then be ground and then be completed. And that thank you very much, is the end of our presentation.